So to ease working with this procedure, we developed an R package called the hypr package. Actually, Maximilian Rabe is the lead author on this. And this can be used to implement this procedure that I just showed you. And I want to present this package to you because I think it's actually a nice way to work with, to implement contrast for the hypotheses that you have in your research design. So it's the way to derive custom contrast matrices automatically from your hypotheses. So what you have to do manually is you have to define the hypotheses that you have. I think that's something you have to do always. If you want to test your hypotheses, you first have to define them clearly. Not always trivial, but that's something you have to do. And then what the package does automatically, it extracts the weights, writes down the hypothesis matrix, converts the hypothesis matrix to a contrast matrix, to the generalized inverse, and then you just have to assign the contrast matrix to the factor and run the linear model. That's again, of course, done manually. But this really tremendously eases working with this setup, with this generalized matrix inverse. So the hypr package is available on CRAN. You just can install it with this command. And there are two important functions that I will mainly focus on. The one function is the hypr function, and the other function is called contrast hypothesis. So for your hypothesis, you can get the contrast matrix. So I will come back to the same examples and show you how to implement this in hypr, how this would be easily done. First, we start with the treatment contrast. Sorry to repeat myself all over again, but now how to implement this with hypr. We define the hypotheses. V1 is equal to 0, and then we compare all the other conditions to the baseline. And the nice thing is that in hypr, we can directly enter these hypotheses. So we call the hypr function, and then hypotheses are entered as formulas. So formulas are characterized by this tilde operator. So the first hypothesis is that M, and then we can call our factor levels by whatever we want. We just say here the mean of x1, we just call it M1. And the first hypothesis states that M1 is equal to 0. That's the first null hypothesis. The second null hypothesis is that M2 is equal to M1, then M3 is equal to M1, and M4 is equal to M1. So each of these is the formula with this curly equal sign, and the different hypotheses are separated by commas. That's all we do. And then we can look at the output of the hypr command. First, what it does, it moves all the terms on one side of the equation so that the other side shows a 0. So 0 is equal to mu1, 0 is equal to M2 minus M1, M3 minus M1, M4 minus E1. Then we see the call of the hypr, the call to the hypr function that we elicited. And now we see the hypothesis matrix, again in transposed form. So each column is one hypothesis, and the rows are the different factor levels. And we can see now for the treatment contrast that we have now seen several times, the hypothesis matrix states that the first hypothesis is just the mean of x1 against 0. The second one is x2 against M2 against M1. M3 against M1, and M4 against M1. So this is our hypothesis, and then it also shows us the contrast matrix. The first column is the intercept, because it's just a column of ones, and then we can see this typical pattern of ones that go down here on the diagonal. The first condition is the baseline, has zeros, and then there's this diagonal of ones going down. We can have a look at the standard treatment contrast. We can see that this is exactly the same matrix that we created here. So we can see that just by specifying the hypotheses, we get all the other information for free by the package. And then we can save this information. We can look at the class of the output. It's a class hyper. And then we can extract the contrast matrix by using this function contrast hypothesis. And then we enter here the output of the hyperfunction. Now here I specified the argument remove intercept equals false, because by default the contrast hypothesis function removes the intercept. Because this is automatically added by R, we don't need it in our contrast matrix. But here I can turn this off, and you can see that the contrast matrix is fully shown. The next step would be to assign this to our contrast attribute of our factor using contrast hypothesis and then this output of the hyperfunction. One change that I made here, up here I used M1 and M2 and M3, but now I changed this to X1, X2, and X3. Why did I do that? Because in the contrast of our factor levels are called X1, X2, X3, X4. And if one thing that the contrast hypothesis function does, it wants to make sure that the contrast matrix is not attributed in a wrong way. So the ordering of the levels should be correct. And to do that, it checks whether the contrast, whether the names of the factor levels in the hyper function are the same as the factor levels in the factor. And if it's not, it throws an error. So you really here, because the factor levels are called X1, X2, X3, and X4, in your call to hyper, you should also say X1, X2, X3, X4. So just you should use the same labels in the call to hyper as the levels of your factor. Only if these are the same, then this operation works. Otherwise, you get an error. Okay, so this is very important. Otherwise, it doesn't work. So one way here to implement this, you can also specify the hypotheses directly in the contrast hypothesis matrix, in the contrast hypothesis function. So you can just write in the hypothesis here, then you just get the contrast matrix. But the hyper function, of course, shows you can check whether the hypothesis matrix was as intended and whether everything works out correctly. This is just the quick form. Okay, yeah, that was, and now we can again apply this, run this model with the treatment contrast, where we have already seen that the contrast coefficients are equal. Then the estimation should also yield the same result. Okay, so that's the workflow for the hyper function. Let's see some again. Let's look at some other examples of how to specify other contrasts with the hyperfunction. Oh no, one more thing. I said before that the generalized inverse allows us to flip back and forth between hypothesis and contrast matrix. You can also do that in the with the hyper objects. First, we create some hyper object with the here for the treatment contrast. So we can see it's a treatment contrast. 2 is compared against 1, 3 is compared against 1, 4 is compared against 1. But now we want to change the baseline level. We want to say that the last row, so X4 is the baseline level of the treatment contrast. So we can implement this matrix. And what we can do now, we can elicit this call to CMAT. CMAT is the contrast matrix of our hyperfunction, hyper object. So this hypothesis of treatment is what we defined up here in the call to hyper. And now we can add our new contrast matrix where the baseline is changed to the contrast matrix argument of the hyper object, and then automatically hyper changes not only the contrast matrix. Now the last the X4 is the baseline, but it also changes the hypothesis matrix. So now we can see that everything is compared to the last condition. The first condition, the second, and the third condition is compared to the last. Okay, so we can also do this inverse transformation in hypr itself. So a lot of information for you. I'm not sure what your current state of mind is. I cannot see you, but yeah, let's see. But with hypr, it's kind of straightforward, I think. So there's a lot of background on that. So how can we apply hypr to get a sum contrast? Let's just play through a few more examples, or the same examples that I showed you before. We said in the sum contrast, we say that the first hypothesis is that the x mu1 is equal to the grand mean, then x mu2 is equal to the grand mean, and mu3 is equal to the grand mean. And we can simply implement that in hypr by saying x1 is equal to the average across all factor levels, x1 plus x2 plus x3 plus x4 divided by 4. Then x2 is equal to the grand mean, and x3 is equal to the grand mean. Then automatically it extracts it rewrites this whole thing. It extracts the weights from these hypotheses, puts them in the hypothesis matrix, and spits out the contrast matrix, where this is how we know the sum contrast. The last row is a number of -1, is a row of -1s, and then there's this diagonal of 1s. We can also test this in our model by saying contrast hypothesis, add this to the contrast, and we get, again, the same numbers that we saw before. Okay, so this is quite straightforward. We just compare one condition to the grand mean, do that for every contrast, and then we get the correct results. Now, how about the Helmholtz contrast? How do we implement that in hypr? Again, we have comparison of the hypotheses to remind you of the Helmholtz contrast. Second, x2 is compared to x1, so mu2 is compared to mu1. Then the average of the first two is compared to mu3, is equal to mu3 by the null hypothesis, and the average of the first three is compared to the fourth mean. And in hypr, we can simply implement that. x1 is equal to x2, x3 is equal to the average of the first two, and x4 is equal to the average of the first three. Yeah. Then we can see the hypothesis matrix. Here you can easily see 2 is compared to 1, 3 is compared to the average of the first two, and 4 is compared to the average of the first three. And now we can see this somewhat more complex contrast matrix that we saw earlier. It's just exactly the same that we constructed before. Yeah, we can actually, I think below I do the test again to be sure that the contrast coefficients are the same, but it automatically spits out this contrast matrix that we have manually constructed previously. Note that in hypr, there's also this argument order levels. So if you do that, it brings automatically the factor levels in the correct order, so that x1, 2, 3, 4 are ordered alphabetically. But you also have this levels argument. You can say levels M4, M3, M2, M1. Then hypr orders these in the order that you specify there, M4, M3, M2, M1, in case your factor has a different ordering than the alphabetical ordering. Okay, this is just an interim, what I wanted to show you. Now we have this custom-made design matrix from our Helmholtz contrast hypothesis. If we apply that to the contrast attribute, run the linear model, we can again see the intercept is the grand mean. The first difference is 10, the second difference is -5, and the third difference is 26.67. So this manual Helmholtz contrast now estimates exactly the differences that we wanted to test, and it's quite straightforward to write this down in this hypr object, and we get the correct matrix. Okay, last step, repeated sliding differences. It's getting a bit repetitive, but maybe it doesn't hurt. So we compare the first to the second to the third to the fourth. We just write this in hypr, second to the first, third to the second, and fourth to the third. We order levels. We see the hypothesis matrix, the comparisons 2 against 1, 3 against 2, and 4 against 3. We see the somewhat complicated contrast matrix. We can again check this looks exactly as the contrast matrix that we have seen before and test the same effects. Again, this example where we have a treatment contrast with the grand mean as a baseline. We set the null hypothesis of the grand mean is equal to 0, and then we compare each vector level to mu1 to the baseline mu1. So we can implement that in hypr just by saying the grand mean, the average across all conditions is 0, and then 2 is compared to 1, 3 is compared to 1, 4 is compared to 1, and yeah, we get again here we see in the hypothesis matrix that the first hypothesis is that the average of all 4 conditions is equal to 0. Then we compare 2 against 1, 3 against 1, 4 against 1. Now we find again, we have this somewhat strange contrast matrix, but if we apply this to our contrast attribute, run the linear model, we can again see that the intercept is 20, that's the grand mean. The first slope is 10, then 0, and then 30, 10, 0, and 30, so it works out fine. So now let's, for the fun of it, create one very custom contrast that is different from the standard contrast that we use. Let's assume we have the hypothesis that we want to compare condition 1, let's say some baseline to condition to 0, whether that's 0. And then we want to, so this would be kind of part of a treatment contrast. Then let's say we want to compare x2 to x1. This would still be in line with the treatment contrast. But let's say now we have a hypothesis that the average of x1 and x2 is equal to x3. So this is kind of what we would expect in a Helmut contrast. And then as a last hypothesis, we state that we expect x4 to be equal to x2. So this is really not in the realm of the standard contrasts anymore, right? Now we have a single, so we have a kind of a mix of different contrasts. But in hypr, it's no problem. We just enter these contrasts. Then we can look at the hypothesis matrix. The hypothesis matrix shows that the first condition mean is compared to 0. Then the second hypothesis compares 2 against 1. The third compares 3 against the average of the first 2. And 4 compares x2 against x4. And if the function computes the generalized matrix inverse, we see that this yields a contrast matrix that is highly unusual. I would have never come up with this contrast matrix if I would have to specify this from the top of my head. So 1 half, 1, minus 1, minus 1. It's kind of a strange contrast matrix in my mind. But somehow it implements these hypotheses. And what we can do now, we can apply this contrast, or we can first extract this contrast matrix using contrast hypothesis, and we can check how are these contrasts correlated. And we see that the correlation here is minus 0.5, minus 0.3, and 1.7. That's kind of in the realm of what we saw in the other contrasts as well. So maybe we would say that should still be fine. So we apply the contrast matrix to the contrast attribute of the factor and run the model. And now let's see whether we got what we expected. The intercept, okay, the first hypothesis was that the intercept is 0. The mean of x1 is 0. That should be mean of x1 is 0, that the difference is 10. So we get an estimate of 10 here. The second contrast said that x2 is equal to x1. That's a difference of x2 is equal to x1. That's a difference of 10. That's represented here. Then the next contrast with the average of the first 2 is equal to the third. Average of the first 2 is 15. The third is 10. So the difference is 5. That's captured. And then the last hypothesis was that x2 is equal to the difference between x2 and x4. Difference between x2 and x4 is 20 and 40. So the difference is 20. So the minus 20 is captured here. OK. So yeah, I think that's that's the hypr package and how you can use it to extract, to design your own contrasts based on the hypothesis that you have. So there's a package there's a paper in the Journal of Open Source Software that also introduces the hypr package and the logic of the underlying logics in this JML paper. Okay, are there questions about this? No, there I see something. You stated orthogonal contrasts have statistical advantages. Could you elaborate? What advantages are these, or rather, how do they translate into hypothesis testing? So if you have independent hypotheses, then yeah, what is a problematic threshold in terms of correlated contrasts? So if you have orthogonal hypotheses, these really test different aspects of the data. So they, if you have correlated hypotheses, they are they are not independent from each other. So you're kind of asking 2 times the same question. If there's a positive correlation between 2 variables and one is significant, then the chances that the other one is significant will also be high if there's a positive correlation, simply because they are not testing different aspects of the data, but they are testing somewhat the same aspect of the data. Then in linear models, the linear models try to really capture the independent aspects of each contrast. So they control for the other contrast when they estimate the contribution. But this control has some limits. So if you have a really high correlation between the contrasts, the estimate might not be accurate anymore. We will see an example for that in the next session for polynomial contrasts, where we can get highly correlated predictors, and we see that the estimates that we get are not accurate anymore. So if you have highly correlated predictors, the estimates that you get might not be accurate anymore. What is the threshold for that? I don't know. I don't want to. I don't know what a good threshold, what a common threshold for that is. Personally, if something is larger than 0.6 or 0.7, I would consider it highly problematic. One thing one can always do is you can simulate data, and you can try to check whether the contrasts get you estimates that are okay. But maybe I would be interested in the audience. I think we have some statistical knowledge in the audience. Is there anyone? Do you have any contributions on these first 2 questions? Maybe there's an opinion there. Anyone? Oh. So one way to approach this is, if you have highly correlated contrast, you can simulate data and then estimate the coefficients in the simulated data where you know what the true effects are, and then you can compare the estimates to the true effect. And so it's important in the end that, so one thing with highly correlated predictors is that that statistical power declines. If two predictors, so because the model tries to capture the individual the contribution of each individual predictor separately from the others, so if they are highly correlated, the power to detect an effect in each of these conditions is strongly reduced. Yeah, I'm not sure what else to say to that.
Sorry, so to see if I understood correctly, I was the one that wrote the question about the orthogonal contrasts. So what you're saying is that if we have factors that maybe or are correlated, or we expect them to be correlated, it would be advantageous to use orthogonal contrasts just because they would be able to account for some of that covariance, I guess, among the factors.
Yeah, I mean, I said before that in the end you want to test your hypotheses, and if the hypotheses are not orthogonal, then the research design is the problem, I would say. So if you specify your hypotheses, in the way that you think that you want to test them. And let's say you notice that two contrasts are correlated 0.90 or 0.95. Then maybe your research, the design of your study, or the design of your experiment does not allow to tease apart the different hypotheses that you want to test separately. So then maybe you have to think about how you can come up with an experimental design or a study design where these questions are orthogonally or more independently varied. You know what I mean? Because I'm not sure. I mean, you can revert to say, okay, now you can change your hypotheses by testing orthogonal contrasts, but then if they are not the hypotheses that you have in mind, I mean, you probably have some theory and you want to test some theory, and this theory might make this prediction and have a certain hypothesis about the data. Then changing the hypothesis that you test is also kind of a strange procedure, because then you're testing a different hypothesis and not the one that your theory proposes. So yeah, in the end, if you have very high correlation, one possibility could be to change the research design to try to have a design where the different hypotheses that you have are more orthogonal to each other, if that's possible. There's also a procedure that I will present in the next session that shows how you can orthogonalize predictors from each other. So that can sometimes be a solution. I will present that in the next session. Okay. Does that answer the question?
Yeah, I mean, I think so, but I was a little bit intrigued by the statistical advantages, but it does make sense that if the hypothesis is not orthogonal, then it might just be a matter of just altering the experimental design. Yeah. Thank you.
Okay. Yeah. Cool. I see in recent examples, ordered levels are set to true. Ordered levels is used. What difference would it make if we don't use ordered levels? So I'm actually, to be honest, I'm not sure what the latest state of the software is, whether ordered levels is implemented automatically or not. What it originally was, so ordered levels brings the levels in alphabetical order. So from top to down in the hypothesis matrix. And in the end, you want to have the same ordering in your contrast matrix. You want to have the same ordering as in the factor that you assign the contrast to. Let's see if I have an example. Yeah, here. Your order levels is true. I'm not sure what the default of hypr currently is. If you said, so originally we had a situation, wait a second. Here, for example, originally we had ordered levels equals false as a default. Then in this situation, when you had x2 first and then x1, then it would here show x2 first and then x1. But it could be that by now, by default, it orders the levels alphabetically. So that's certainly happening when you set order levels equals true. Okay. But if you set order levels equals false and you enter the x2 first, then x2 will be the first column, the first row, x1 will be the second row, x3 will be the next, and x4 the last. Okay, so if you set order levels equals false, then you just get, you can see it here in the factor, in the names of the factor levels that are here presented in the contrast matrix, in the hypothesis matrix. And you just have to make sure that this ordering is the same ordering that you get on the contrast, on your factor. So your factor, if you look at the contrast matrix for that, it also has some ordering of the levels. And here it's ordered alphabetically from x1 to x4. And then in hypr, you should have the same ordering, and you can achieve that either by setting order levels equals true, or by this levels command. I think you showed it here, by adding levels equals, and then you can specify the order directly. But I have to pass on the question, what is currently the default? I think Max changed it. I think that ordering levels is true by default, but I'm not 100% sure. Okay.